last year when ChatGPT first came out, and we're at BentoML, we were all very excited about what it can do. But at the same time, we were worried that such powerful technology is only in the hands of a few. But then we think to ourselves that if LLMs follow the path of any previous open source software that we know, such as operating systems and relational database, then in just a matter of a few years, there could be really compelling, really containing contenders coming out from the open source to challenge this position. But we were completely wrong, but in the sense of that it didn't take a few years, it only took a few months. Back in February this year, Meta released the first version of Llama for research purposes. Its weights got leaked in shortly 1 week after the release. But in the hindsight, this is something like a blessing in disguise because it inspired a sequence of models such as Alpaca and Vicuña to build on top of Llama for more innovation. And we'll remember MPT for its large context size at the time, and Falcon as a model briefly took over the best model surpasses Llama as the best model briefly. And then starting July this year, when Llama 2 releases, this time with a chat model of very different sizes, then the cycle just repeats again. I think what we learned from this is that the open source LLMs are innovating really fast, and the capability is getting better and better. I suppose to advance the slides. Yeah, so its capabilities are advancing better and better. We all want to be able to leverage these LLMs in production. However, to use this LLM in production is not as easy as just downloading the model to your laptop and starting it locally. You won't be able to get the efficiency and the performance that you need in a production setting. And that brings us to our topic today, is how to productionize open source LLMs. And I am Sheng. I'm from BentoML. I'm actually based in California. It's 4:30, almost 5 in the morning. When I picked the time slot, I didn't realize the time zone was in UTC. So I guess something to learn. But I'm overall very excited to be here to share with you our experience building productionizing open source LLMs. So from our perspective, there are 3 reasons that you want to run LLMs in production. It's control, data privacy, and cost efficiency. So before diving into any of these, we'll first look at factuality. Factuality is very important. It's the opposite of hallucination, which we're all very familiar. And it's one of the biggest problems that LLMs are combating because it leads to misleading information, incorrect answers. And an LLM is not useful when it hallucinates. So how well do open source LLMs perform in terms of factuality? And this study came out a few months ago by Anyscale. It's comparing summarization accuracy of Llama 70 billion versus GPT-4. And it's using a multiple choice of forms of answer to pick the right answer of summarization. I won't get into the details, but the gist of it is that human performance at 84%, GPT-4 outperforms human at 85.5%. Llama 70 billion model is not that far behind, is at 81.7% accuracy. All in all, this is a single example. It doesn't represent the full picture, but it gets us an understanding that open source models are getting there, are getting closer to the proprietary ones. And factually, I think if we use them in the right way, we can really extract a lot of value out of them. So with that out of the way, let's talk about the first advantage, is control. So control is in the form of fine-tuning the model and managing the format of the output exactly in the way that you want. You can either do a full parameter fine-tune or do a low-rank adaptation, or more well-known as LoRa. To fine-tune a model, you actually don't know a whole lot of data. A few hundred records will do, and a handful of hours of running on GPU will get you a pretty good results. If you don't feel like fine-tuning your own model, you can use a pre-trained model that's available on Hugging Face. Currently, there are over 36,000 text generation models, and it's increasing at a very rapid pace. I think a month or 2 ago, I was looking at it, it was only at 22,000. So it increased by 30% or so in just a matter of a few months. And when should you be fine-tuning your model? And to answer this question, we look at 3 case studies. The first one is a functional representation, which translates natural language into function calls. So you can think of it like converting an instruction into a function call. The second is a SQL generation, which also from a natural language, converting to a SQL statement against a very specific schema. The last one is GSM-AK, which these are grade school word problems, which requires more context and reasoning. And we have, we're evaluating 4 different models in here. The red model is Llama 70 billion, green is 13 billion, the blue is 70 billion, and the pink bar is GPT-4. And within the Llama models, you can see different shades of the color. So at the very bottom is the performance. The darkest shade represents the performance of the model when it's not fine-tuned. So we're strictly talking about the baseline model. The second darker shade represents when it's fine-tuned using LoRa. So you can see that the performance gets a lot better, and the lightest shade represents the full parameter performance. So the takeaway here is that fine-tuned models perform much better than the baseline model. The baseline model is barely getting anything accurate, but the fine-tuned model is getting close to 100%, at least for the first and second tasks. And what's interesting is that these models outperform GPT-4 in terms of accuracy as well when it comes to first and second case, the functional representation and the SQL generation case. However, when we need a lot of reasoning in the problem-solving space, these fine-tuned models do not even get closer to GPT-4. So when should you be fine-tuning a model? I guess the answer for now is that when the reasoning task, the task require low reasoning, fine-tuned model performs pretty well, outperforms GPT-4 even with smaller parameter sizes. That brings us to the next advantage, which is data privacy. So our users in our open source community come and ask us for help to deploy their models, deploy open source models for them. They worry that calling a third-party API will lead to leakage of their sensitive data information. They worry that their data will be used in training the next iteration of the LLMs. As a result, their sensitive information is exposed. Where running open source model, the model is well within your virtual private cloud, so your data will never leave your network boundary, so you know that your data will not be used for other purposes. Transparent training data usually comes as a part of the open source model itself. You can also disclose that to your stakeholders and your clients, so you're not worried getting into potentially, I guess, copyright infringement problem. Lastly, if you run your own model, you're taking control of the availability, so you're not susceptible to the provider outages. The third advantage we see is cost efficiency. So commercial LLMs, we all know, charge by tokens and context sizes. GPT-4 is 8,000 tokens, and if you want larger context sizes, doubles the cost. And running fine-tuned models is still up to 6 times more of the baseline model cost. And this cost can really add up if you're running an agent-based application or chat-based applications where there are multiple rounds of iterations that goes between your application and the model server. However, if you run with the open source LLMs, you only pay for the hardware that you incur. You pay for the GPUs basically, and there is no extra cost for running fine-tuned model. If your traffic can saturate a single GPU, a single VM, I think the cost efficiency aspect can be much favorable situation compared to calling a third-party API. One very important aspect is that you can choose to run much smaller parameter size LLMs. Not all problems requires the GPT-4 to solve. As we've seen previously, Llama 7B and 13B, once they're fine-tuned, they get pretty accurate and they even outperform GPT-4. So with smaller tasks, smaller models, you can potentially gain additional cost efficiency. But as we talked about previously, there are challenges that running these models in production, and we see there are 5 different aspects: operability, scalability, throughput, latency, and all of these eventually contributes to cost, which is answer the question, how much do I need to spend for running these LLMs? So first, let's talk about operability. LLMs are called large language models because they have large number of parameters, and each of the parameter is represented typically as a floating point 16-bit data type on GPU or 32-bit on CPU. And to calculate the memory footprint, you can simply multiply the parameter size by 2 in terms of gigabytes of memory needed, because each parameter is required 2 bytes to load into GPU memory. So what we can see is that Llama 70 billion model will require 140 gigabytes of GPU memory to serve. That simply exceeds A100, even with the 80 gigabyte version of the GPU device. So we cannot easily fit a model on a single GPU card. Additionally, just fitting the model weights in the GPU memory is not is just to scratch the bare minimum of the requirements for GPU memory. You also need to reserve enough GPU memory for running inference, actually ideally more than the model weights itself. So that's the first challenge, operability. Second is scalability. As we all know, GPU today is still very scarce and they're expensive. You want to pick the right GPU type for running your inference. If you're running smaller models, ideally you deploy onto fractional GPUs. And if you're running larger models, as we've seen previously, we want to run them on multiple GPU devices. With traffic scaling up and down, you want to scale the instance up and down with the traffic. And if there is no traffic, you ideally want to scale to 0 to conserve your cost. Utilizing spot instances can be a trick for CPU serving because GPUs is really hard to come by, let alone the spot instances. But this comes with the challenge that you want to be able to dynamically load and unload the model with and serve the model on the instance with the best availability. Cold start is a problem that we commonly see because these models are very large, and streaming those models from the model repository down to the machine takes a very long time just because the sheer size of the model. And cold start also comes in the form of that you need to wait for the cloud provider to provision you an instance and waiting for that instance to join your cluster. We talk about container image download and model downloading takes a very long time. Then we still need to load the weights into CPU memory and GPU memory. All of that takes a very long time. And this will require a lot of optimization to solve and accelerate the cold start delay. The third problem is throughput. So throughput is typically measured by token per second. And as English language, each token roughly represents 0.7 word in English. For other languages, the ratio varies. It depends on the tokenizer that you choose to use. In the traditional ML settings, the way to improve throughput is to use this technique called batching. However, batching in LLM is very complex and inefficient if you just take it as a static way, because LLMs don't just run iteration once. It runs multiple times. Every time it generates a token, it runs it one round of iteration. And that's why when we use ChatGPT or other types of LLMs, you see words appear on screen word by word, because LLMs are running iteration one at a time. And the length of the generation is undeterministic at the beginning. We don't know, so that we have to reserve the maximum amount of memory possible. And to add on top of that, once a sequence has finished generating, we cannot return it back unless the whole batch is complete. So in this case, we see on screen, sequence 3 cannot be returned, even though it finished generation right away, until sequence 2 has completed. So all of these, in the traditional batching sense, adds to complexity for batching for LLMs. We'll talk about potential improvement in how we can accelerate throughput in LLM using better batching techniques. Lastly is latency. Latency is easy to understand as a challenge. There are two types. As in the LLM settings, we can think there's perceived latency. This is applicable when your end consumer is a human being. So for example, like a chatbot, all we need to do is exceed the average reading speed of a human. It's roughly 5 tokens per second. As long as we exceed that, the perceived latency gets very low, even though it takes longer time to generate the full body of text end to end. The next type of latency is end-to-end latency, and this is more applicable if the consumer is a program. So such as an LLM agent, because the agents needs the full text to be able to move on to the next text. So even with streaming, for example, streaming the token back to the LLMs, we're not going to solve the end-to-end latency problem. So at BentoML, we are a open source unified AI application framework. We are here. We want to help teams in the world, machine learning teams in the world, deploy all kinds of models, including LLMs. But looking at this framework, we first have to define what an AI application is. Try to think of the way that you want to build ChatGPT, but with open source models, where you can provide the chatbot with an image that you took, for example, in your living room, and you want to ask the chatbot for assistance to replace a certain object or change the color of the wall. And for this application to work, you need a sequence of model to work in conjunction to complete this task. First of all, you need an LLM to understand the user intention and then generate the responses. And then you need a set of image generation and models, such as segmentation model, which is able to carve out the different objects on the screen, in the picture, a clip model to understand what the different objects are, and the text-to-image model, such as Stable Diffusion, to replace a certain object with a different one. And to be able to support this model, this architecture of running multiple models in the same application, BentoML come up with this architecture that works with different model runners. So model runners, you can think of it as a abstraction of model that can run in independent hardware and scales independently based on traffic. So an LLM is probably running on like a more powerful GPU, but image segmentation can probably run on a weaker GPU. This way, you can get best hardware utilization at the same time cost efficiency out of it. And we have an API server layer that orchestrates the traffic and request to the different backend model inference and orchestrates the calls and responses back to the user. At the same time, BentoML packages dependency, environment, source code, model, and configuration in the same distributable artifact, call it a bento, so that you can achieve consistent behavior between development time and production. So what you see in the development time is actually what you get in production. That's a proposition of this architecture. But as we've seen before, just by solving the ML ops problems, be able to deploy the model does not. We still have the set of challenges with LLMs, and that's why we built. The another project, OpenLLM, to help deploy and operate LLMs in production. And we'll look at what OpenLLM is. At the simplest form, it's can be started as a service with a single command line by providing the architecture, in this case Llama, and the model ID. Here we have a Llama 2 7 billion chat model. We can see this in action. When it's run, we expose an HTTP endpoint. We can provide it with a prompt. In this case, we're asking what's the concept of time, and together we provide a set of LLM configs, and we can see the response generating back in the stream fashion in real time. So beside running as an HTTP server, OpenLLM can also, in the HTTP server, it also expose OpenAI compatible endpoints. What this means is that if you have already written an OpenAI application using OpenAI client, all you need to change is the base URL from an OpenAI URL to the OpenLLM deployment URL. You don't need to provide the API key because we're using open source model here. None of the other code needs to change, and it should just function. The API is fully compatible with OpenAI. It also can be exposed as a Python library, so we can import OpenLLM as an LLM object. We can run a generate iterator in an async loop, so we get all the generated text back iteratively. OpenLLM integrates with LangChain as an LLM object. So if you have a LangChain application, you can replace any LLM objects with OpenLLM. Same for Llama Index. The integration is native. you can replace any LLMs in Llama Index with OpenLLM implementation. And at the end, of course, OpenLLM works with BentoML. We'll dive a little bit deeper at the end of this service file if we have time at the end. So after seeing what OpenLLM can do, why do we want to use OpenLLM? The first benefit comes in the wide range of models that it supports. So all the latest and greatest models, architectures, you can pretty much expect is supported within OpenLLM itself. And to use it, you only need to provide the arguments with the model ID and the model architecture. In this example, I'm only showing the command line arguments, but you can think about the Python SDK access with LangChain and with Llama Index works in a similar way, but with Python code. The second advantage is quantization. So we saw how large language model take a whole lot of GPU memory to run because we are using floating point 16-bit data type to represent its weight. But there are techniques, there are quantization frameworks that can reduce the model weights to 3 bits, 4 bits with lower precision. And we can comfortably fit a Llama 70 billion model under 40 gigabytes of GPU memory. That means we can run Llama 70 billion in a single A100 GPU. And that's pretty huge. And with an 80 gigabyte model, we can save comfortable enough GPU headroom for running inference as well. And to be able to use the quantization framework, you just have to pass in the quantized parameter. In this case, we can use GPDQ. Next, we talked about the traditional static batching wasn't the best fit for LLMs. That brings us to continuous batching. Continuous batching allows us to asynchronously schedule the newly arrived request into the batch without having to wait for the previous batch to complete. So in this case, we can see as soon as S3, the sequence 3 finishes, we can schedule sequence 5 to run without having to wait for sequence 2 to complete. And this is all thanks to our collaboration and integration with VLLM. VLLM integrates, builds the continuous batching and page attention, which is more efficient use of memory by default. And OpenLLM comes with VLLM support out of the box for if there's a GPU available. The next optimization is model parallelism. This is the practice to fit a very large model onto multiple GPU devices. You can do this either through pipeline parallelism, which is split by layers, or tensor parallelism, split the weights within each layers. Worth to point out that model parallelism introduces additional communication overhead because your multiple devices needs to talk to each other, which ultimately impacts your performance. But this is useful when you want to run a large model without quantization. And to run them on multiple cards is the only way. And to support that, you can pass in the worker per resource. The value is the inverse of the number of cards that you want to run. 0.25 means we're running this model on 4 devices. Lastly is token streaming. So what it means is that we'll return the token back to the user as soon as it becomes ready. And this helps perceive latency because user can consume the data right away when the consumer is a human. And this is built in out of the box with the stream generate stream endpoint. With all of that said, this famous paper came from Google back in 2015 says that the ML code for running inference is only a small part of the huge ecosystem of ML ops. We still need to solve all the challenges that comes in the form of ML ops. But luckily, OpenLLM built with BentoML, which comes with the best practices built in. So BentoML is fully customizable with Python. Therefore, it integrates with all the Python ecosystem and tools, just within a Python way. And as we mentioned before, BentoML packages the model source code configuration as a Bento artifact, so we can achieve a consistent behavior between development time and production time. With the bentos, we can do version control with the bento store support, and BentoML comes with observability out of the box, so you don't have to implement metrics, tracing, and logs. It automatically is established as part of the framework. And the bentos can be containerized into standardized OCI compliant images, so you can deploy that to any platform that supports image and container deployment. Means pretty much all the public clouds with Kubernetes and Docker support. How are we doing on time? 3 minutes. Maybe let's quickly dive into the architecture and how the service code looks like. So quick reminder, this is the architecture. We have different model runners, an API server. So with OpenLLM, the LLM can be imported into BentoML as a runner, and the runner can be established as part of the service that we see in line 4 and line 6. And in the API definition, which this will be later exposed at the HTTP endpoint, developer can define any behavior using that LLM endpoints. So in this very simple case, we're just passing in the input text as a prompt to the LLM and return the result back to the user. But you can imagine if we're building a chatbot where we need to understand the intent and maybe call a second model within the API, we can all do that because it's just simple Python code. Once we have this service, we can run BentoML build. This is how we get a bento from what we've seen previously. And you can run bento ML list, and we'll see all the bento that you have stored locally. And the bentos can be pushed to a remote location as well, similar to how we manage Docker images. Okay, I think we're right about time. Let's conclude. So today we talked about advantages of using open source LLMs. Then we dived deeper into the challenges of deploying these open source LLM in production. And at the end, we talk about how BentoML and OpenLLM the optimizations built in there can help us solve these problems. And thank you. Thank you for your time, and thank you for PyData for giving us this opportunity. So what's on screen is my personal LinkedIn and the GitHub page for BentoML and OpenLLM. These are fully open source project with Apache 2 license. You can use it for your purposes. Yeah, thank you.